So today we are going to talk about the number systems. Okay, so let's first understand how do we define a number, or what is a number. I say number is a ordered collection of symbols. Ordered collection of symbols. Okay, why is it ordered collection? It is ordered collection because 123 is different from 231. Okay, these are different. Okay, therefore the order is important, right? A number has basically two parts. It has an integral part and it has a fractional part. Okay, so obviously we know what it is. If I say 123.56, then 123 is known as the integral part. Everything that comes before this is called as a radix point. Okay, so everything that comes before the radix point is part of the integral part of the number, and everything that comes after the radix point is part of the fractional part of the number. So now that we have defined what number is, let's understand what do we mean by a number system. Okay, I say number system is something that allows me to specify the allowed symbols. Okay,
so let's understand what do we mean by allowed symbols. Allowed symbol means the number of symbols that we can use to form a number. For example, in our day-to-day life we use decimal number system, okay, and decimal number system has 10 allowed symbols. Okay, so what are these 10 allowed symbols? These are 0 to 9. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are symbols, okay, which we use to form a to form a number. A symbol in a number system is called as a digit. Okay, what is a digit? Digit is a symbol in a number system. Okay, so we used 1, 2, 3, 5, 6, which are symbols, to form a number. Okay, so that was the interpretation of allowed symbols by specifying number system. Okay, and the number of allowed symbols is known as the base of the number system. Base of number system is the number of allowed symbols. Number of allowed symbols. Okay, our decimal system has 10 allowed symbols, therefore it is having a base of 10. Okay, I'll just take this circle off and I'll just write it as base equal to 10 for decimal number system. So let's look at a general number from any given number system, okay, of base k. A number from number system of base k. Okay, So my number would be something like this. It is going to have the first digit, second digit, third digit, okay, so on. It's going to have, let's say, dn minus 2 and dn minus 1. So how many digits do we have right now? We have digits from 0. Let's use a different color. We have digits from 0 to n minus 1, which is n digits. Okay. Right. And then we have a radix point. And we have the fractional part. Let's call it as d minus 1, d minus 2, d minus 3 up to d minus m. So how many digits we have in the fractional part? We have 1 to m, which is m digits in my fractional part. Now, this is a number in the given number system of base k. Okay. Now let's understand what would be the equivalent value of this number in base k in decimal number system. Okay. So the equivalent value in decimal number system of this number is equivalent decimal value, okay, is equal to, it is going to be, since we are having a base k, we are going to use k as the weight. So what do we mean by the weight? Weight is the multiplication factor. Okay, so what I have here is, I'm going to say this number is equivalent to d0 into k raised to 0 plus d1 into k raised to 1 plus d2 into k raised to 2 plus d3 into k raised to 3. Okay, I'm going to do this, add these products up till, what do we have? dn minus 2 into k raised to n minus 2 plus dn minus 1 into k raised to n minus 1. Up till this point, this is the equivalent integral value of this number in decimal number system. Okay. After this, let's see what is the equivalent fractional value. The equivalent fractional value is, I'm going to just write plus with a different symbol so that you're able to distinguish between the fractional and integral value. My fractional value would be d raised to d minus 1 into k raised to minus 1 plus d minus 2 into k raised to minus 2. We do this until we reach d minus m into k raised to minus m. Okay. So this is my equivalent decimal value. Okay. This is similar to tens, hundreds and thousands concept that we have learned in our school. Okay, so if I have a value like 123.56, how do we represent it? It is basically this 1 into 100 plus 2 into 10 plus 3 into 1 plus 5 into 0.1 plus 6 into 0.01, right? This is 100 plus 20 plus 3, which is equal to 123, plus 0.5 plus 0.06, which is 0.56. Okay. If you look closer to this expression, you're going to realize that this is same as 1 into 10 raised to 2 plus 2 into 10 raised to 1 plus 3 into 10 raised to 0. Anything raised to 0 is 1, okay? Plus 5 into 10 raised to minus 1 plus 6 into 10 raised to minus 2. Okay? So, if I express this using index, this is the first index, second index, third index, then the minus 1 and minus 2. Similar to what we have done over here. 0, 1, 2, 3. Okay, this is 3. I think I have written it as 4. This is 3. Okay, 0, 1, 2, 3 in this direction, and minus 1, minus 2, minus 3 in this direction. Okay, so this is my equivalent decimal value. So why did I multiply this using weights as 10? I did this because I said that 123.56 is a number system in base 10. Okay, how do we specify the base of a number system? We specify it like this. I say 123.56 and within brackets I specify the base 10. Okay, so this represents a number in base 10. Okay, had I done something like this, 123.56, then this would be a different number. Okay, this would be a number in base 8. Okay, and its value too would be different. So 123.56 in a number system of base 8 would be 1 into 8 raised to 2 plus 2 into 8 raised to 1 plus 3 into 8 raised to 0 plus 5 into 8 raised to minus 1 plus 6 into 8 raised to minus 2. Okay, so this is going to be 64 plus 16 plus 3 plus 5 by 8 plus 6 by 64. Obviously this value is going to be different from 123.56 that we got when this number was in decimal number system. So this is not equal to 123.56. okay, let me tell you one more thing over here. In this kind of representation, we call this number as most significant digit. Okay, the number in the extreme left is known as the most significant digit, and the number in the extreme right, okay, is called as the least significant digit. Okay, we are talking only about the integral part of the number. Okay, now let's look at binary number system. Okay, what is a binary number system? Binary number system is a number system having base 2. Okay, so my k is equal to 2. Okay, so what are the number of allowed symbols? The number of allowed symbols is 2, and these allowed symbols are 0 and 1. Okay, only these two symbols are allowed to form a number. Okay, this is my binary number system. These symbols are called as bits. Okay, so if I have number like this, let's call it as D0, D1, D2 till Dn minus 1. Okay, then all these D0, D1, D2 are bits, and my D0 is the least significant bit. Okay, and my Dn minus 1 is the most significant bit. Okay, another terminologies that we are going to learn over here is a collection of 4-bit is called as a nibble. So what is a nibble? Nibble is collection of 4 bits. Okay. Similarly, we have another term over here which is known as byte, and my byte is a collection of 8 bits. Okay, I think I have missed 4 over here. Okay, this is a collection of 4 bits and byte is a collection of 8 bits. Okay, so now let's first look at how to convert a decimal to binary. Okay, conversion from decimal to binary. Let's suppose I have a number. Let's suppose I have number as 56. Okay, this is a decimal number and I want to find out the equivalent number in binary number system. Okay, what is this equivalent number? So what do I do over here? I successively divide 56 by 2 and store remainders, okay, at each step. And then what I do, I just write the remainders from last to first. Okay, and then write the remainders from last to first. So let's take an example to understand what these steps are. Okay, we already have 56 in decimal to be converted to binary. Okay, so first I'm going to successively divide 56. Okay, so let's do like this. I divide it by 2. What do I get? I get 28 over here and I get 0 over here. Okay, here this guy, or rather this column, is the remainder column and this column is the quotient column. Okay, then let me just proceed further. Again I have 2. What is the quotient? 14. And what is the remainder? Remainder is 0. Okay. Again divide by 2. Quotient is 7. Remainder is 0. Right? Again divide by 2. Remainder is 3. 3 into 2 is 6. Okay. And remainder is 1. Quotient 3. Remainder 1. Okay. Let's proceed further. Divide it again by 2. Okay. My quotient is 1. My remainder is also 1. 2 into 1 is 2 and it leaves me a remainder of 1. Again I am going to divide it by 2. I see that my quotient is 0. 2 into 0 is 0 and I am left with 1, which is my last remainder. Okay. Now this was the first step. Successively divide by 2 and store remainder at each step. Okay. Let's not call this 56. Let's call it as successively divide the number. Okay. Successively divide number. Okay. So my second step is write the remainders from last to right. Last to first. Okay. So I am now going to write it from last to first. 1 1 1 0 0 0. So my 56 in decimal is equal to 111000 in binary. Okay. So I have already given you the equivalent decimal value representation over here. Okay. So if this is the equivalent binary value, then its equivalent decimal value should be 56. Okay. So let's verify this. Okay. So how do we verify? We verify it like this. Let me just write the indices over here. Okay. So I have my number as 111000. Okay. This is my binary number. I'm going to write the indices. Indices is 0, 1, 2, 3, 4, 5. Okay. So my equivalent decimal value is going to be something like this. 0 into 2 raised to 0. Just realize over here what I've said. Equivalent decimal value for base k. Okay. In binary number system, what is the base? Base is 2. Therefore my weights is going to be in terms of powers of 2. Okay. Plus 0 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3 plus 1 into 2 raised to 4 plus 1 into 2 raised to 5. Okay. So what is the final value? Final value is only 1 into 2 raised to 3 plus 1 into 2 raised to 4 plus 1 into 2 raised to 5. Okay. So this is 2 raised to 3 is 8, 2 raised to 4 is 16 and 2 raised to 5 is 32. Right? And what is 32 plus 16? It is 48, and 48 plus 8 is 56. What did we begin with? We began with 56 and we ended up with 56. Therefore, this is the right binary representation. So this was my converting an integral part of decimal number into an equivalent integral part of binary number. Okay, now let's understand how do we convert a fractional part of decimal number. Fractional part of decimal number. Okay, the process is very similar, so I am going to copy these steps. Okay, I have it pasted over here, right? This was step number 2. My first step earlier said successively divide n by 2 and store remainder at each step. This is going to be modified as successively multiply. Okay, successively multiply n by 2 and store remainder part is going to be modified as and store fractions at each step. Okay, my second step was this is and store integers at each step. Okay, store the integral part at each step. Okay, and the second step is modified as write the remainders from last to first. Here we have write the integers not from last to first but from first to last. Okay, so let's see what we are doing. So let's take a number. Let's suppose I have this as a number in decimal and I need to have an equivalent binary fractional number. Okay, so how do I proceed? Successively multiply n by 2. Okay, so let's start. Let me have my number over here, 0.625. Okay, multiply it successively by 2. Okay, what do I get over here? I get 0.625 into 2 is 1.250. My step says successively multiply by 2 and store integers at each step. What is the integral part over here? The integral part is 1, so I'll store 1 over here. Okay, so over here this is my product and this is my integer part and this is my fractional part. Okay, integral part. Okay, now we are going to repeat this step successively until I get a 0 as fractional value. So I'll just add one thing over here. Repeat this until 0 is got as fraction. Okay, and over here, when do we stop? Successively divide n by 2 and store remainder at each step until 0 is got as quotient. Okay, just understand, we have 0 as quotient over here, that's why we stopped. Okay, so let's continue our successive multiplication. So after the first step, the fractional part is this 0.250. I'm going to multiply it by 2. What I'm going to get? I'm going to get 0.500. And now what is the integral part? Integral part is this, which is over here. Similarly, this, which is over here. Okay, that's it. Yeah, this over here. And what is 0.250? 0.250 is this. Okay, so next I am going to write over here 0.500 multiply by 2. What do I get? 1.000. What is the integral part? Integral part now is 1. Okay, so this 0.5 goes to here, or rather make it like this, here, and this 1 is over here. Right? Now that we have 000 as fraction, therefore we stop. Okay, the next step is to write the integers from first to last. So what I'm going to do, I'm going to write it as 1 0 1. Okay, so my 0.625 in decimal is equal to 0.101 in binary, right? Let's just verify that this is correct. 0.101, right? Let me just write the indices. This is 0, this is -1, -2 and -3. So what is the equivalent decimal value? Equivalent decimal value is 1 into 2 raised to -1 plus 0 into 2 raised to -2 plus 1 into 2 raised to -3, which is equivalent to 1 by 2 plus 0 plus 1 by 8. Okay, 1 by 2 is 0.5, 1 by 8 is 0.125. So my answer is 0.625, and this is what I started off with. So this is the correct answer. Okay, so that was about converting a fractional part of a number into the equivalent binary number. But just understand one thing over here. You might not always get 000 over here. Okay, for example, if my number was 0.624, let's suppose I had 0.624 and I wanted to get the equivalent binary number. Okay, so what I would do, I am going to write it like this. Okay, multiply it by 2. I am going to get 1.248. My fractional part is 0.248. My integral part is 1. Again, I am going to write the fractional part, multiply it by 2. What I get is 0.496. Fractional part is 0.496. Integral part is 0. I'll take my fractional part over here, multiply by 2. I'm going to get 0.992. Okay, my fractional part is 992. My integral part is 0. Okay, multiply this by 2. I get 1.984. My fractional part is 984. My integral part is 1. I'm going to multiply it again by 2, what I'm going to get is 1.968. Fractional part is 0.968, integral part is 1. Just realize over here, let me just create a table out of it. Okay. So this is my table, and what I have over here is, this is the product, this is the fractional part, this is the integral part. Okay. So just realize I am not getting 0 in my fractional part of the product. I am doing it again and again and still I am not getting a 0. In that case, what I do is I just select the precision that I want. Okay, so I can say, let's suppose I say that I want this number with the precision of, say, 3 decimal places after decimal point or after radix point. Okay, so in that case, what I'm going to write is, I'm going to say that my 0.624 is 0.624 is equal to 100. I'm just going to take first 3 numbers in binary with a precision of 3 decimal places after radix point. If I wanted precision of 4 decimal places after radix point, I could write it as is equal to, I'll take the first 4 integers 1001, 0.1001. Okay, and similarly if I wanted 5 decimal place precision, I would write it as 0.1001. and what is the last? Yeah. So in this way I can go on proceeding like this until I get my required precision. But just understand, this is going to be an approximate value. We are never going to find out a correct value if we are not getting a fraction in which we have 0 in the product fraction. Okay, until we get 0 in the fraction of the product, we cannot say that this is a correct equivalent value. Okay, these are all approximate values. This is precision of 3 after decimal places, precision of 4 after decimal places, and this is precision of 5 after decimal place. So how would we convert an number having both integral and, let's suppose, fractional part into a binary number? So let's suppose this is my number. What is the equivalent binary number? The process is, first, I'm going to write step 1, convert integer part. Second is convert fractional part and append. Okay. Step 2 is convert fractional part, and finally step 3 is append So what is step 1? Convert integral part. So what is the integral part 56 in binary? It is, where did we do that? Yeah, it is 11100. Okay, so first step, step 1, 11100 in binary. Step 2, convert to fractional part. Let's suppose I want precision up to 5 decimal places. I'm going to write it as 0.10011. Okay, my step 2 is 0.10011. Okay, 0.10. Just understand, here I am not going to use the 0 over here. I am just going to write it as 0.1011. Okay, and the final step is append. So what I get is 111000, and to this you append the fractional equivalent binary number, which is 0.10011. So this is the equivalent number that we are talking about. 56.64 in decimal is equal to 111,000.10011 in binary. Now let's look at the concept of ones complement. Okay, what is a ones complement of a binary number? It is simply the number in which we replace zeros by ones and ones by zeros. Okay, so if I have a number like 010010 in binary, then its ones complement would be replace 1 by 0 and 0 by 1. So what I'm going to get? I'm going to get over here 1 0 1 1 0 1. 0 is replaced by 1, 1 is replaced by 0, 0 is replaced by 1, again 0 is replaced by 1, 1 is replaced by 0, and final 0 is replaced by 1. Okay, so this is the ones complement of a number. And what is the twos complement of a number? Let's see. Twos complement of a number is ones complement of the number plus 1. Ones complement of the number plus 1. Okay, so let's suppose I have my number as 0 1 1 0 1. Okay, so what is the twos complement of this number? My twos complement of this number is going to be, first I'm going to find out the ones complement. What is my ones complement? Ones complement is 1 0 0 1 0. Okay, and to this I have to add 1. So I'll add 1 to this. What I'm going to get is 0 plus 1 is 1. I'll just tell you what addition, binary addition looks like, but for the sake of twos complement over here, just understand this is the equivalent binary addition. So my 2's complement of 0 1 1 0 1 is 1 0 0 1 1. This is the 2's complement. Okay.